everyone, Jeremy Blum here with our third installment in the Arduino tutorial series. This week I'm going to be talking about EE, or Electrical Engineering Basics. This is just things like voltage, current, and resistance, understanding Ohm's law, voltage dividers, voltage regulators, things along those lines. All the basic stuff that you need to get an Arduino hooked up to some real circuitry and doing some cool stuff. So for each example I go through, I'll talk about how it relates to the Arduino and an example of when you would need to use it when interfacing some electronics with the Arduino. And it should be a lot of fun, so let's get started. Okay, let's talk Ohm's law. Ohm's law is probably the most important law you'll ever learn about electrical engineering. It's very simple. All it says is that voltage equals current times resistance. Resistance is measured in ohms, current in amperes or amps, and voltage in volts. If you want to learn a little bit more about current, I'll refer you to Jerry Ellsworth's video on the topic. It's really quite good. So let's see an example of this law in action. Let's say we have a 5-volt battery, positive and negative terminals, and a 100 ohm resistor across it. What's going to happen is that current's going to flow through this circuit, but how much current? Well, using Ohm's law, it's very easy to determine. Voltage equals current times resistance, which means current equals voltage over resistance, which we get by dividing both sides by R. Therefore, we can say 5 volts over 100 ohms, as we were given in the problem, is going to give us 0.05 amps, or 50 milliamps of current through this circuit in the direction shown from positive to negative. And that's it. That's all there is to it. That we just determined how much current is flowing through that circuit. Okay, now let's talk about a practical application of this. LEDs. Everyone uses LEDs, and especially in the Arduino, they're very, very useful for debugging and many other purposes. So a lot of people always ask why you can't just hook up an LED from 5 volts to ground. Why can't you just send power through and it lights up? Well, it will light up, but we're going to run into a serious problem here. LEDs, the way LEDs work is they work on a diode IV curve, which you can see here. Basically what that means is that after V drop, or after a certain point, what's going to happen is the diode allows any amount of current available to flow through it, which is good for many circumstances, but if it's a light emitting diode, we're going to have an issue because, or if it's any diode really, we're going to have an issue because we're allowing it to draw unlimited current from the source. And the Arduino supply can only store so much current. So what that means is this is going to suck up all the available current, and it's going to kill your battery very quickly, and the LED is going to burn very bright but also get very hot because you're sending so much current through it, way more than it's rated for, and that'll kill the LED pretty quickly. So it will light up, but we're going to run into some issues. Most LEDs are designed to run with around 20 milliamps of current flowing through them. So let's see how we can design the circuit so that the proper amount of current is flowing through the LED, which will ensure we get a long lifespan and a reasonable battery life. To do that, we're going to put a resistance in line with the LED. And you always see this. In fact, I did this in the video last week, and here's the reason why. By putting a resistance in line with it, we can ensure that a proper current is going through the line from 5 volts to ground, and therefore that there's not too much current going through the LED. So let's figure out what resistance we want that to be. If we have a 5 volt supply, and we want 20 milliamps of current going through the LED, which is a pretty standard amount for it to glow at a good brightness, we'll want to use Ohm's law to figure out what the resistance should be to accomplish that. So resistance equals voltage over current. We have 3 volts left because 2 volts will drop over the LED on its own. So that gives us 5 minus 2, which is 3 volts to drop over the resistor. So we want to drop 3 volts over the resistor, and we want 20 milliamps of current to be going through it. So if we divide that out, we get that the resistance should be 150 ohms. And of course you can go higher than that. It'll make the LED a little bit dimmer. You can even go a little bit lower than that, but you usually don't want to go too much lower. You'll be drawing too much current and hurting your battery life. And that's it. So let's see an example of what this means in an actual circuit. So I have an LED here hooked across our voltage and ground lines from the Arduino, which is running at 5 volts. Let's see what happens to the current that's going through it when I plug it in. Whoa! 158 milliamps? That's way too much. That's drawing basically the maximum that the Arduino can output. And you can even see that the LED is growing yellow instead of green because the spectrum of the color has changed due to the massive amount of current that's flowing through it. Let's unplug this before we damage anything. Now I have a 150 ohm resistor, as we calculated in Ohm's law before, hooked up with the LED in the Arduino. Let's see what happens. LED turns on. This time it's actually glowing green like it should. And we're at just about 20 milliamps. Perfect. Ohm's law predicted it just as we expected it to. Now we're going to talk a little bit about pull-up and pull-down resistors. So if you remember in last week's tutorial, we used a button, much like this one, hooked up to pin 8 on the Arduino, same as we do here, but we had a pull-down resistor between the pin on the Arduino and ground, and it was a 10K resistor. Now we just have the button hooked into 5 volts, and the other end goes right into pin 8 on the Arduino. You would think that when I push the button down, you would get the 5 volt signal on the Arduino pin and would go to 1, which it does. But the issue is going to come in when I'm not holding the button, and you would think it would go to 0. But what's really going to happen is that the pin is going to kind of float at some random variable that can be influenced by random electrical noise in the area, and will cause the Arduino to get false readings of 0 and 1 and switching back and forth between them. If you look at the code I'm running on the Arduino right now, it's very simple. Basically all it does is we have a button hooked up to pin 8. It's set as an input. All I'm doing here is allowing it to communicate with the computer via serial. We'll cover this a little bit later on in more detail, but basically it just allows us to send information to the computer terminal. And all that I'm doing here is I'm sending that information on a different line each time, and it's going to read the state of the button pin and then wait for a second. So in this terminal window right here, it's displaying each second, it's changing this value. Right now it's showing a 0 like it should. And when I hold down the button, it's going to change to a 1, as we would expect it to. But let's see what happens when I'm talking about the noise. So I just released the button and it's still displaying a 1. You can see it scrolling up the screen there. And I bet, yep, simply just messing around with the wire a little bit will occasionally get it to turn to a 0. That's not right at all. Electrical circuits should not do that. And so the reason behind that is we're just basically causing random electrical noise that's causing the pin to float up and down and either go high or low, which is not what we want. So let's try this circuit now again with a pull-down resistor in place. We now have our 10K resistor in place, and essentially what this resistor is doing is setting a default value for the button. What that means is when the button is not depressed, the resistor pulls it down to ground. But when I push the button, since the resistance is so high to ground and so minimal to 5 volts, we're essentially going to get a 5 volt signal on pin 8 of the microcontroller, which we can see if we look at the screen now. If I push the button, it goes to 1, just as you expect. I release the button, and it goes back down to 0. And unlike before, wiggling this or touching it with my finger or anything like that isn't going to jar it from 0. It's going to stay exactly where we want it to. Perfect, and that's how pull-down resistors work. Pull-up resistors work in a very similar fashion, except they pull it up to 5 volts as a default instead of to ground. We could do that too if we wanted to. Next topic is voltage dividers. So voltage dividers are something that we're going to use a lot whenever you're basically dealing with any kind of analog input to the Arduino or any other microcontroller. So let's talk briefly about how they work. Say we have a 5 volt signal and we want to get any voltage between ground and 5 volts out of it. It's very easy to do, and all you actually need are 2 resistors. Basically you hook up 2 resistors between 5 volts and ground and take a line out between the two. And based on what you tune R1 and R2 to, using the voltage divider equation, which I'll explain in a second, you can get V out to be any value between ground and 5 volts. The voltage divider equation is pretty simple. Basically all it is the voltage that you get out here is equal to whatever the original voltage, in this case we'll be working with 5 volts, that voltage times the bottom voltage over the sum of the 2 voltages. So it's kind of like a ratio. You're dealing with this over the whole thing. So let's talk about an example here. Let's say that we have R1 is equal to R2 is equal to 100 ohms. So both of these are 100 ohm resistors. Every time when you have 2 resistances of the same value in a voltage divider, what you'll find is that the voltage out will end up equaling exactly half of what the original voltage was. Let's see why that is. If we have 100 ohms from R2, and then these two are both 100 ohms, that's 200 ohms together, that's 100 over 200, which is 1/2, times 5 volts, the original voltage, which gives us 2.5 volts. Perfect. Now, let's talk about a practical application of a voltage divider. The main application of a voltage divider is for inputs as sensors and sensors and potentiometers into an Arduino. They have a lot of other inputs. Maybe you need a voltage reference or things like that, but generally you want to use a voltage regulator when you want to draw a high amount of current out of them. When working with sensors, though, they work perfectly. So the simplest possible example is a potentiometer. The way a potentiometer works is basically there's a little wiper that goes back and forth along a resistance value, usually about 10K, that you hook up between 5 volts and ground. So what that wiper is doing is it's acting just like our line up here, except now there's only one resistance and it wipes up and down between the two, changing the resistance on the top and bottom. And this essentially gives you a voltage selector that you can then feed into the Arduino and use to check a voltage. So if the wiper's all the way at the bottom, it's basically connected to ground, and if the wiper's all the way at the top, it's essentially connected to 5 volts. But when it's in the middle, you end up with a voltage divider equation. And I'll show you how that works in just a moment. Another example is when you want to hook up basically any other kind of sensor to the Arduino. Most sensors work as being variable resistors. So if, for example, we have a photodiode which changes its resistance along with changes in the amount of light in the room, which we represent like that, we can hook that up through a voltage divider circuit. So once again, we'll have 5 volts. We usually use about 10K as the other resistor, and then our variable resistor right here. So as the light in the room changes, this resistance varies, which affects the voltage divider equation, this guy, and we therefore get a different voltage out. So as the light in the room varies, we get a different voltage out of our line here, which then gets fed into the Arduino's analog inputs, and we can read that value between 0 and 5 and do something interesting as a result. So let's see an example of this in action now. Here I have a simple potentiometer, usually abbreviated to a pot, and I have it hooked up to one of the analog input pins on the Arduino. Now we'll be talking a little bit more about analog input in some future episodes, but basically we have our red connector on the pot, which goes to our 5 volts, ground, which goes to ground as I showed in the diagram, and then the middle one is the one going to the analog input pin on the Arduino, which is analog input 0. The Arduino has 6 analog inputs, each of which can read values from 0 to 1023 depending on the voltage from 0 to 5 that you give them. And you can change the voltage reference too, but we'll talk about that a little bit later. So, let's see what happens when I turn our potentiometer. We can see as I turn the pot, the value goes from 0 up to 1023. And then I can turn it back down the other way, and the reading that the Arduino gets scales down back to 0. The program that I'm using to do this is almost identical to the program that we used before, except now it's a potentiometer. It's hooked up to analog input pin 0. This is different than the set of digital pins, but it's still 0. It's still an input. We're still initializing our serial connection. The only difference really is that we're doing an analog read instead of a digital read, which reads the value in from 0 to 5 volts and assigns it a digital value from 0 to 1023. And if you're more interested in analog-digital conversion, I talk about that in the TechBits episode, which is linked below. The last thing we're going to talk about today is voltage regulators. We just talked about a voltage divider as a great way to get a lower voltage out of your circuit that's providing a higher input voltage. But if you want to use something that draws a fair amount of current and is using a fixed voltage, then a voltage regulator is the way to go. The reason being is that voltage dividers will give out above a certain output current and will start to fall off in performance and the voltage that they can provide, whereas voltage regulators up to a certain current are guaranteed to always output that voltage despite the input current, as long as it's above a certain value. This is an example of what a voltage regulator looks like in real life. It's generally 3 pins, and the 3 pins match exactly these 3 pins. The leftmost accepts a signal above about 7 volts up to 17 volts. The middle one goes to ground, and the third pin goes to a 5-volt rail. So what this is doing, this is taking 9 volts in this case. We're going to hook it up to a 9-volt battery, and it'll spit out 5 volts. And the great thing about voltage regulators is that even as the battery dies or as the voltage decreases from 9 volts to about 8, it's going to continue providing a constant 5-volt signal, which is perfect for powering motors or anything that you want to be at a constant voltage. The other key thing to remember when using voltage regulators is that you always have to use these decoupling capacitors on both power rails. The reason being is that the capacitors essentially act as a reservoir for electricity that holds the excess as the voltage regulator does the conversion from higher voltage to a lower voltage and removes ripples and just basically makes sure that you have a clean output voltage that's perfect for working with. Let's see what happens when we put this voltage regulator into a circuit. Here we have our voltage regulator hooked up in a circuit. Voltage regulator is right here. Note the heat sink that dissipates excess heat. We also have 2 decoupling capacitors as I described in the diagram earlier. This is all hooked up to a 9-volt battery on one end of the voltage regulator, and on the other end I have a multimeter showing the voltage output. If we hook up the battery, we can see that the voltage goes straight up to 5 volts, just like we want it to. And a disconnect, and it goes right back down to 0. And if, regardless of the voltage level of this battery, as long as it's within the acceptable range designated by the data sheet, we'll always get 5 volts out of here, which will be perfect for powering a lot of projects. Note that as this battery discharged, we'd be getting a different voltage if we were using a voltage divider, because it would change the input voltage and therefore the output voltage would change accordingly. Okay, that about does it for this episode of our Arduino tutorial series. I hope you guys enjoyed it. As always, any documentation or anything associated with this episode is available on my website, jeremyblum.com. There's a description and the link below. Also, don't forget to head over to Element 14 and submit your project to the Element 14 Arduino contest that's running up until January 31st. So submit your project. I really look forward to seeing everything that you guys have been working on. It should be a lot of fun. And that's about all I have for this week, so I will see you guys next time. Thanks a lot for watching. Thanks to Element 14 for helping me to sponsor this video series. They were kind enough to provide a lot of the materials that I'll be using to create these tutorials. Feel free to go visit their website at arab4science.com. Check out their community, which is a great place to talk to people about electronics, the Arduino, and basically anything else engineering related. And they also have a store where you can buy a lot of the parts that we'll be using in these videos.